Welcome. So please join here. There was some problem in the other link. So once you guys join, we will start. Okay. So could you confirm my voice is coming to you clear? Welcome Akshay. Welcome Pooja. Welcome SVS. Please confirm you guys can hear me clearly. Once you comment, we will start our session. So guys, welcome. Basically, we are starting a free live session on quantum mechanics for CSIR NET examination, for GATE exam, for JEST examination, for IIT JAM and all other MSc entrances. It will also help, but it will mainly focus on CSIR NET and GATE examination. Okay, thank you Sonu. Welcome. Thank you Vimula Venkatesh. Welcome Ipik Santanu. So this is our first lesson, and we will start shortly with quantum mechanics. So if you guys have any question, any queries, you guys can ask. Any question from your side? Thank you, Santanu. I am also excited to give you live sessions on YouTube, and that will obviously help many students in various subjects. So in upcoming days, we will try to stream other subjects also live on this YouTube platform. So obviously the free education, as much as we can provide, we will try our best. Welcome Ram. Welcome other students joining live. So please share with your friends quickly so that others can also join. So this is first lecture, so we will start shortly. Okay, we will wait for few minutes and then we will start. I am good, Ram. How are you? Yeah, Akshay, we will try to finish all quantum mechanics syllabus in this lecture series. So any question if you have, Pooja, Ram, Akshay, SVS, anything, Santanu, so that we can discuss initially. Then obviously we will start our topic. We will start with wave function from quantum mechanics, and then subsequently we will discuss all other topics. So this will be obviously a free session for all the students, so there is nothing to worry about, and we will try to take regular classes in the evening so that you can attend regular session, make your notes. So please share quickly with your MSc juniors and all other students so that they can join live, or recording they can obviously see after that. Okay, so now I'm starting the first topic of our quantum mechanics course. So in this course, we'll mainly target for CSIR NET and GATE examination. Welcome, Anamika Devi. Okay, so you guys can ask your questions in the meantime, also in between our session going on. Okay, so first we will start with wave function. So as all of you guys basically knows, this represents a particle in the space, in the three-dimensional space, and it is denoted as psi. So basically it is a representation of the particle in we have three-dimensional space. So here the main thing is the probability distribution comes in the picture. So we'll talk about it in detail also in upcoming minutes. But initially, if I talk about the dimension of wave function, what are the dimensions of wave function in different space, 2D space, 1D space, or 3D space. So it is very important question for GATE examination, and the dimension. So how to get the dimension of a wave function? So it's not that directly you will say the dimension of a wave function, but a very important phenomena from the Born approximation. And what this Born approximation suggests? This suggests that in the entire space, this space can be a 1D, 2D, or 3D, the probability function, which is denoted by psi square, if I take three-dimensional space dx, dy, zz, its probability should be 1. So this psi square is basically your probability density function. Very important. So from the statistical interpretation from the Born, you guys can say that this condition will be followed for a wave function. So you see the probability PR, if you are in three dimension, you can represent it as a pxyz. Okay, this will be equal to psi square, as we are mentioning here, which is our probability density. So if we are in a three-dimensional space, for the probability that sum of all the pi's, that should be 1. This is a very basic thing. If you are having a it's a particular case in which different events can happen, the all events happening probability, if you sum them, that will be obviously 1, not less, not more. So if we are in three dimension, now we can say that in three dimension, if we can say that probability density should be equal to, or you can say in other words, that probability per unit volume. So if you say per unit volume, that means 1 upon L power 3. L is length here, and that should be equal to probability density, which means psi square. And now from here, you can get the dimension for a wave function in three dimension. How? So if you see this relation, simply that psi for three dimension will be calculated as you can see L power minus 3 by 2. L is the length here simply. So this is the dimension of wave function in 3D. So please do note this, and if you have any question here, you guys can ask in your comments. So I will answer once I get your comments. So yeah, Shantanu, surely it will be helpful for both the students. And thank you, Pooja. Yeah, so upcoming sessions we will try other subjects also. So if you have any question from here now, you guys can ask. So you guys should write also. Those who are new student, you should write your notes, and then it will be helpful for you to once you revise the things. It will be very helpful. So it always important to note down the things and make proper notes, because it will be a complete course. So there will be nothing much left after you attend all these sessions. So in the evening 8 p.m. or 9 p.m. this session will be regularly live. So now if we move forward in the two dimension, in 2D case, welcome Vinod Kumar Ravi, very good evening. So Vinod, we have just started. So if you have any question for 2D, what it will be? Probability per unit area, you can say. So here if we see, it should be 1 upon L square, and in this case the dimension will turns out to be psi for 2D will be simply length inverse. And similarly you can easily now calculate for one dimension that psi square should be probability per unit length, and that will turn out as 1 upon L only. So from here we can see the dimension of wave function for a one dimension system will turn out to be L power minus half. So these are the three interesting results we are getting now, which is very simple to calculate, but yeah. Okay, so do note quickly, and then we will talk about wave function little more. Yeah, very good, Sonu. Yeah, Pooja, we will try to have a daily session. Welcome, Lalit Devra. We will try to have daily sessions so that you can get much regularity in the making notes and all these things. So I hope you are done writing with this. So now the next thing is, a wave function should be admissible. You all know, for bound state and for unbounded state, the wave function should have certain criteria that we will talk in a different sessions. But just to understand initially that what type of function you will say it's okay for a particular particle, you can apply it. So what are the certain limitations or certain conditions that you should know? So admissible, or you say in other words like well behaved, well behaved wave function. So what are the criteria for this? Can you mention in comment box quickly? Can you mention any criteria for a wave function to be admissible? Quickly in the comment box once you get. I'm waiting for your response in the comment box. If you can mention quickly. Yeah, very nice. It should be single valued. It should be continuous. Very good. Prakash and Lalit. It should be continuous. And also it should be finite everywhere in the space. And third thing, for an admissible wave function, it should be differentiable. Okay. So now Lalit is also and Prakash is also mentioning about vanishing at extremities. Yeah, it should vanish at extremities, but for a well-behaved wave function, it is not necessary that it should vanish at the extremities. It will vanish for other conditions like bound state wave functions and all. So you can write like vanishing at extremities or infinity. Extremities means at the end point. So and square integrable. So those things will apply when you talk about the bound states and unbounded states. Okay. So in both the cases, like bound states you have or unbounded state you have a condition that wave function should be first admissible. So these three conditions basically should be followed for the wave function to be well behaved. Finite everywhere is there, differentiable and single valued or continuous also. So now if you have a suppose nth order, if you have nth order differential equation, differential equation which can be like this. So if you have this equation, its solution will be it should be single valued and secondly the differentiable conditions should be there. So the differentiation y or the y dash, y double dash and so on till y n minus 1, this differentiation should be existing and continuous. So for example, if I talk y equal to x thing, So if we only focus on the single valued, is it single valued? Y equal to x? Quickly comment down. Is it single valued? So if you draw y equal to x, this will turns out to be like this. So what does the single valued means? Single valued mean is, for a single value of x, there should be only single value of y existing, not more than that. For a single value of x, y should have also a single value. It should not be like this. For example, if you say any random curve where it could be like this, this kind of curve, just for an example. So here you can see, for a single value of you know for a single value of x, suppose here you have a y value here as well as here. So you see this is not a single valued. Do you get the point? Yeah, you can take an example of x square also. So no, correct. So this could be the scenario. So now I will basically give you a question and you have to quickly solve it out. That I will give you particular graphs and you have to identify that wave function which you can say like admissible or not. So now till this point, if you have a question, you guys can quickly put it in the comment box. So I'm writing a question for you. The admissible wave function is, your options are this could be a plot of any kind of differential equation. So we are not actually worried about what kind of relation between y and x. Only you have to see the graph and you just have to tell me which could be a admissible wave function according to you. You can say psi x also here. Or y, anything. The last option is okay. So can you quickly comment down your answers? Welcome Kaushik Sinha. Very good evening. So can you quickly comment down? So I'm writing the other question also once I get your comments. Okay, so there is a slight delay once I speak this and I get your comments. So in those seconds I can use to write the second question. Okay, so here you have to answer. I will make the combinations and you have to identify which combination is basically admissible wave functions combinations. So first option is, wait a second, so and the fifth combination I'm making now here is, okay, could you answer quickly in this? Audio is coming to you guys clearly, all of you or not? So in the first question, if you see, this could not be a correct answer. In the first question, if you see, this could not be a correct answer. Why so? Because if you see on this is not finite everywhere. You see why? This is tending towards infinity. We discussed a point like vanishing at extremities, but it should not be infinity. So here, for a wave function to be admissible, it should not goes to infinity, it should be finite. So here you see, this is a kind of sin x variation. So you see, this is sin x variations. Obviously it is continuous, you can see there is no discontinuity, and it is also differentiable, obviously, if it is following like trigonometry relation, and single valued everywhere. You see there is no double value of y or a wave function x, psi x, with respect to x. Here you see again the same condition coming, infinity. And here the problem, as we discussed in the last slide, at a single value of x there are two values of psi x available. So this is not single valued. So here this is gone, this is gone, and this is gone. This is the right answer, and I think you all are mentioning that. Okay, and the admissible wave function is, so here you have six different wave function: 10x, sec hyperbolic, 1 upon x square plus a square, this exponential of minus x square, and x square with exponential of minus x square, and exponential of x square. So here, if you see the 10x, if you remember the 10x graph, that is not finite, it goes to infinity. So this is not obviously admissible wave function. Sec hyperbolic plot, if you draw yourself, I am giving you this as a homework, like drawing all these things. Okay, I will not draw all these things, but sec hyperbolic, this is Lorentzian, this is exponential of minus x square, it is a Gaussian function, and this is with x square with Gaussian function. So this will also lead to the admissible wave function condition, but this is exponential of x square, which will be basically going to infinity again. So this and this will be gone. So here b, c, d and e only will be the admissible wave function. I think you got it. If there is any problem in this, you guys can quickly mention, then we will move forward. A very important point for today's class is upcoming now. Anything you have to ask now, you can ask quickly. Otherwise, we will start now is classical allowed region and classical forbidden region in terms of wave function. And now you know the definition of wave function, you know the admissibility of it. So we can now proceed with the next thing. Please share this also with your friends so that they can also join in this live stream. Please share, because it's just the beginning. So as soon as they join initially, they will get the more benefits. Most of the you guys know me, but you are already done some courses on some other platform. So this is a free platform for all of you. So those who missed anything, you can revise it here. And obviously, whenever I get time, I will try to be very regular. So it is a good thing for you that everyone get a free lessons on CSIR NET also. Because on the free platform you will get some lectures, that is okay, but getting a detailed lectures series is not that available. So we will try to make this happen for you guys. Okay, so moving forward now with the topic. Classical allowed region and classical forbidden regions. Any question, guys? Anything to ask? Kaushik, how is your preparation going on? Any update on your results or anyone else? Sonu Gore, Prakash, any update your this gate exam? How was there, guys? All of you appeared for the gate exam, I hope, and I hope you will get good results. So the total energy is a combination of kinetic energy and potential energy. So here you can see the kinetic energy is obviously E minus V. Okay, so with the kinetic energy, now we will have few interesting combinations. So all of you guys know the one dimension Schrödinger's equation. One D Schrödinger's equation, time independent if we talk. So according to this equation, you know that d2 psi over dx square is equal to 2m upon h cut square v minus e psi. This equation you guys know very well or not? Quickly tell me. This is the one equation you guys know from your BSc days, I think. So this is basically also nothing, it's just a postulate. We will discuss about it. The Schrödinger equation, how to get this equation also we will talk a little bit. So if we have, suppose the total energy E greater than potential energy V, then here we will get a total term as negative. And if the total energy is less than the potential energy, here we will get a positive term. So this is a very interesting thing. to define the classical allowed and classical forbidden region. So can you mention what should be kinetic energy, for a classical allowed region? What should be the kinetic energy for a classical allowed region? Here E should be bigger or V? Can you comment down quickly? It's very simple. What should be the condition for a classical allowed region? Can you quickly comment down? Are you guys getting voice? If there is some problem in voice, low voice, you guys can use headphones or earphones. Okay. I'm not getting your response on the comment box. Do you guys know what is the condition? The very simple condition is that kinetic energy should be positive for a classical allowed region. So here you can simply say E should be greater than V. And here in this condition, you will get T greater than 0. So kinetic energy is positive. Very simple condition. So now if you have a wave function greater than 0, so here you see the multiplication of psi also is there. So what is wave function also? You can draw in the space. So what if you have psi positive, what if you have psi negative, what will happen? And then by combination what kind of pattern we will get? That is a very interesting analysis now. So first thing, if I take that psi is greater than 0. So here you can see that d2 psi over dx square, that will be what? Here we can see that E is greater than V. So this will turns out to be some negative value with respect to this. This will be a negative value multiplied by a psi. So psi here we are considering positive. So this turns out to be that this d2 psi over dx square is less than 0. And if double differentiation is less than 0, suppose psi at x equal to x1, you just take a point so that you can differentiate it with other condition. So psi is positive at x1 and this double differentiation is coming out to be negative. So this point psi x equal to x1 is a minima or maxima? Simply maxima. And if you take a condition that psi is your negative less than 0 at any point, suppose x equal to x0, then what you will say with respect to this is negative and this will be also negative now. So you can directly say that d2 psi over dx square will become now positive, and that is psi x equal to x0 is what? A minima. simply a minima. So now with the help of these two conditions, we will draw an interesting you know plot. But before that, you can take any other point where psi is 0. What will happen if you have wave function 0? What will happen if you have a wave function value 0? Quickly comment down. Also, you can like this. I think on the YouTube there are a lot of features. So I actually don't know much, but yeah, subscribing, liking, and all these things, and sharing, these three things are very important, to get the success in this course. Because if I provide lessons and this does not reach to the students, many students, so till that point it will not be a successful try. So it should reach to a number of students. So it is your responsibility, guys, that you share with your juniors and make this stream successful. And I am very much sure that you will do that. Any comment, guys? Now should we move forward? Quickly. So now if we have next thing, that is wave function equal to 0. So if wave function is equal to 0, then obviously d to psi over dx square is equal to what? 0. So with that you can say that psi will be what? Ax plus b, a linear behavior. Okay, d to psi over dx square will be equal to 0. If you multiply any positive or negative term with 0, obviously it is 0. So now we have seen different scenarios. Wave function value psi x with respect to x. We have taken 2 points. Suppose I mention x1 here and x0 here. So we have seen in the last slide that if we have a positive wave function which is at x equal to x1, the d2 psi over dx square is negative, and that point, that particular point x1 is a maxima. Is a maxima means what? When a point is maxima, if this is a point, this will be called as a maxima when? Only if the wave function get decrease from left and right of it. I think you get the meaning of this. This will be a maxima only if wave function is less than in the left side and the right side of the point. So here you see that at x equal to x1, the wave function will have in nature kind of this. So this will be a point of maxima, and from the left and the right side of this point, the value of the psi x will be less. Okay, now we have taken another point x0. So in the x0 you can see here that double differentiation is positive and this point is a minima. So what does the minima means? Minima, simply if a point is minima, so this will have a minimum value and the right and the left side of it will have value more than this value for the wave function. So then only this point will be considered as a minimum. So here x0 is giving you the minimum of the wave function when psi x is negative. So here you can see this point will turns out to be minima for it. Now obviously it will be 0 at some point. When you connect this, you see this will be 0 at some point here. So you see the nature of this wave function now. If you take many points, this will be turns out to be like this. So this is what? Oscillatory nature. This is the oscillatory nature of the wave function. So here we have a clear conclusion. Here we have a clear conclusion. See, this is psi ax plus b is coming from this condition. If somebody is joining late and don't know how, so when you solve this, this will give you this value. So here we have a clear conclusion that wave function is oscillatory in nature. Wave function is oscillatory in nature when it is classically allowed. So in the classical, very important point, in the classical allowed region, the wave function is always oscillatory. Very important conclusion. So do note down quickly. And now we will talk about the classical forbidden region. So आप लोगों को आवाज़ तो आ रही है ना? कमेंट करके बताइए जल्दी से, क्योंकि यहाँ पे आपके कमेंट्स नहीं आ पा रहे हैं. इज देयर ए प्रॉब्लम? हंड्रेड सब्सक्राइबर हो जाने चाहिए आज ही के दिन. 100 सब्सक्राइबर हो जाना चाहिए. 97 तो ऑलरेडी है, तो ओनली 3 लेफ्ट. सो सब्सक्राइब ऑल्सो. Okay, so this journey is obviously start from 1 and it should not be like 100, 500. It should reach a more higher number. But obviously it will take time, it will take efforts, and obviously your support. So now moving forward, and second condition is for classical forbidden region. What should be the condition for classical forbidden region? E less than V should be there and kinetic energy should be negative. So with the negative kinetic energy, we will take different condition for wave function. First simple condition is psi, Okay, thank you Lalit. So psi should be greater than 0. That time, what will be the value of d2 psi over dx square? So that is obviously, with the help of this you can get. See, this is the equation you have. This time kinetic energy is negative, so E is less than here V. So this is a positive term, and if wave function is also positive, then d2 psi over dx square will also be positive, greater than 0. And that means what? You can take it as a like suppose any point you can mention, like x equal to x1. Again we can mention it like x equal to x1. So what this x1 will be, maxima or minima? This time opposite, this will be minima. And similarly, if you take wave function negative now at any point, suppose x equal to x0, as we did in the last allowed condition, similar things you just have to do now. It's very easy. So d2 psi over dx square is negative this time, and that will lead to psi at x equal to x0 is a maxima. So can we quickly draw it? We can also mention that third condition, if psi is 0, then also again we will get a linear variation of the wave function ax plus b. So this you can also quickly write down. So now with the help of this, we can conclude with the graph that with wave function psi x, we have 2 points x1 and x0. So now we have taken at x1 wave function positive, but that point turns out to be a minima from this. This point is a minima when wave function is positive. So when this point will be minima, you know very well the left and right side should be more valued than this point value, and here x0, as we mentioned, is a maxima. So if it is a maxima, the nature of the curve will be like this. So what does this gives? This gives you a simple information that if you just have a function like this, you don't have any oscillatory nature. You can clearly see there is a clear difference. There is no oscillatory nature. Okay. For oscillatory nature, there should be a continuity like this. Then only you will say oscillatory nature. So here a very important conclusion. This is your psi greater than 0. This is your psi less than 0. So the important conclusion is, in the classical forbidden region, the solution or you can also say the motion, like oscillatory, non-oscillatory motion, or motion is non-oscillatory. Non-oscillatory, very important. Quickly do write. Okay. Any problem till this? You guys can quickly comment down. So this is the basic introduction class to the wave function, and many other things still we need to do about the wave function. So quickly write the things and then we will proceed. So we will end this session with a question. I will give you a question, and with that we will end our session after that. So this is just a beginning of this full quantum course. In the function This question has been asked in some net examination. Pnx exponential of minus x square of a real variable Pnx Pnx is a polynomial of degree n. The maximum number of maximas, okay, the maximum number of maximas, or you can say extremas, this function can have. Very easy question, but little bit tricky also. You can say also solution, maximum number of solution this function can have. So very well it is like 2-degree polynomial, 2 solution, 3-degree polynomial, 3 solutions are there, like that. So if this is a function Pnx with the multiplication of exponential of minus x square, what will be the correct answer here? Can you quickly comment down? The subscriber count should reach 100. This is very important figure, guys. We should achieve today itself. Okay, so here if you see that what could be the answer, possible answer for this, so let's have a solution. If I draw exponential of minus x square, what will be its graph? Very well known to all of you guys, like this. Okay, now Pnx is a polynomial, so this could be anything. Pnx, which is a polynomial, this could be anything. So we can take a simplest polynomial, suppose like just a 1 degree x. So if I now have a new function x multiplied by exponential of minus x square, here what will be the result? Pnx equal to x will have one solution, which could be like x value, anything. But now if you multiply it, what could be the graph? So at the low values, y equal to x will be dominating, but at the higher values exponential nature will come out in the domination, and the graph will turns out to be like this in the both sides. Okay, so we have seen that number of nodes and the solution. What is the solution here? Oh, sorry, what is the maximas here? Not the solution. The question asked here is the number of maximas. What is the number of maximas in this? Number of maximas or extremas. You can see in this graph there is only one maxima. What is the maximas here? there is one here, there is another here. So what is the answer here? 2. So here the polynomial degree is what? 1. N is 1, but the extremas is 2. So what is the answer here? This could be n plus 1. If you have further, increment, there will be 1. If you have 2x square here, there will be 3 extremas. You can draw that. Okay. So here you can say that exponential of minus x square is contributing 1 maxima and other is coming from the polynomial. Okay, so if here I take 1 only, if I take in the multiplication, that is a polynomial of order 0, degree 0. So 0 plus 1, you can say here 1. So n plus 1, because n is the degree of this polynomial. So answer will be n plus 1. So I hope you get this. So कैसा लगा आज का लेक्चर्स? उम्मीद है समझ में आया होगा सब कुछ. ओके, so please share this with your friends, and if you have any query from the lessons today, we have discussed the many various things regarding the wave function. So if you have any queries, you guys can now ask. Okay, so we can have these lectures in English or in Hindi also. I will try to use Hindi in between also. So not a language problem, it should be. So this was the first lesson. I enjoyed giving you the detailed thing about the wave function, and the next lecture will be tomorrow, same time 8 p.m. we will meet on 26. Okay, so any query guys you have regarding this, you can always ask. So please share with your friends. Tomorrow live session link I will send to you all guys as well, so it is very important. So thank you all, take care, have a good night.